One day when colliding two particle systems together, I kind of noticed an interesting patterns emerged, and also as well the particles each formed their own blocks of separate from each other rather than mixing together. And I realized that this was actually due to the collide width, the self-collision width on the particles being less than the collide width with the other particles. So it was more minimal for the particles to cluster together, yet they still wanted to be pulled through each other, which was kind of a surprising effect. Here's a version of that where the particles are also additionally attracted to each other. So these are both these two particles each are liquid simulations, and they've got some surface tension, and they're attracted to the other particle system. So they try and pull together, yet at the same time they're trying to hold together and hold their own shape as well. And interesting thing about this is that I never tried to create this behavior. It sort of emerges out of the composite behavior of the two things. You get a fundamentally new kind of behavior, and I find that extremely interesting when that happens. Another thing is that if I take this and then create a mesh out of it, so I mesh out the particle surface, I get this shape. And to be honest, I can't say if it is for sure because this is somewhat irregular, but it's very reminiscent of the surface called a gyroid, which was discovered by Alan Shun in 1970. And the actual gyroid has some interesting properties. I can't say if this really has the same properties, but it doesn't have reflection symmetries. It has no straight lines in it. I think that's pretty clear here. Sort of interesting as something that emerged out of something completely different. And I could see with fluids, if you could use this kind of behavior with different fluids, and that you could use it to construct maybe useful materials out of the juncture of the two fluids. This was a kind of a fun structure I created. I've got this little script that I call make loopy, and so we could create let me create a polygon torus, and we'll just try running the script on it. This script, all it does is it does like iteratively does the bridge tool between random polygons, and bridge tool is kind of fun. So I called the script make loopy, and so you just select an object and do make loopy and give it a number of times. Let's say 30, and let it run. And then it creates these joins. These tend to look more interesting if you put on surface smoothing. So you can run it any number of times and just create any random object, and you can get pretty cool shapes fast. Here's a simulation that's a fluid simulation where I've got fluid flowing around an object and then turned it into lines. So to do that, created a particle system, ran the particles through the fluid, and then there's a script on High-End 3D which will let you turn particles into curves. Then once I had the curves, I converted them to paint effects, did paint effects to poly, and then rendered out the result with some global illumination to see the effect. Here's another image, this time with transparency. And it's kind of fun, the sorts of shapes you get with fluid motion and visualizing them in this fashion. Okay. Now this is a cloth simulation. It doesn't look like cloth, I know, but you can make the cloth, the elements, fairly rigid. So these all these cubes are all part of one cloth mesh, and then I create a max distance constraint between them with between all points, and use the drop-off on the max distance. So basically the vertices are attracted to other vertices. And then there's noise on the wind noise, and so that is sort of like the temperature in the room. So this is trying to simulate a crystallization, and you can vary the rate at which the temperature gradually gets cooler. You can see the color shows the coolness here. And if you cool it down slowly, you'll get more large block crystalline forms, and if you cool it down quickly, it tends to just clump together in random forms. So again, kind of an interesting thing emerging out of just simple points being attracted to forms, and you get either crystalline shapes or random structures over time. The Swedish artist Eskator X, I hope I'm saying the name right, he created this drawing machine, quite large actually, that uses pendulums, and I thought it might be fun to try and recreate it using Maya Dynamics. So I'm using some end cloth nodes with constraints here, and then in order for it to draw on the paper, I've got a 2D Maya fluid, and then the point of the pen has an emitter that is emitting into the fluid, and it's a non-dynamic fluid, so that it just simply remembers the trace of what moves through it. As well, we now have, in 2012, we properly track the motion of the emitter on the emitting, so we get nice connected lines, even though it's a small emitter that's moving far apart. So it's kind of interesting the shapes you get with this. And you can try different starting points. So I could go back to the beginning and maybe move a pendulum, and then run it and see how it changes the resulting drawing. There's all kinds of different configurations you can play with doing this, and the neat thing is that once you come up with a configuration, you could then build it. So it's sort of a way of testing different things that you might do. Here's sort of the one that a little bit more complete there. Let's look at another one. So the interesting thing here to me is that we start with something fairly simple, just two pendulums. One on its own is fairly boring, but the two together interact, and they can create unexpected art out of very simple, a very simple behavior and initial conditions. In this simulation, I've got two particles, and they're both emitting into a three-dimensional fluid node, again one that's not dynamic, and they're attracted about a center point. That center point has a gravity field that pulls them around, and so they orbit around the center point. And then the second particle is attracted to the first, so it follows it as it orbits. And again, sort of a spirograph type principle, but with kind of planetary orbits. Here's that same sort of simulation, but in this case I've made the fluid dynamic, and the particles have a little push on it as they go through, using the inherent motion on the particle fluid emitter. And again, we get interesting effects. This is a hardware render as well of the fluids. We've kind of improved the hardware draw in 2012. Here's a soap bubble film simulation done with 2D fluids in Maya. Soap bubbles are an interesting form of complexity that you get from the turbulent 2D fluid motions on top of the bubble surface. Now the bubble surface is very constrained. The fluid can only move in 2D on the surface. It's constrained because it's such a flat surface. And so you get swirly, typical 2D fluid motions, which can look quite interesting. Sort of like on the surface of the atmosphere is pretty much a 2D type of solution. Now, the other thing interesting about a bubble is that you get diffraction effects from the thickness of the soap film. So because it's close to the wavelength of light. So based on the thickness, the hue of the color gets, different colors get destructively interfered with. And so you get a rainbow effect based on the thickness. So the density model in the fluid simulation is a good model for the thickness of the film. And so we can just map the density to color, and then the color in this case isn't color of the shading, but if we look at the finished animation here, it's color of the specularity, or the reflected color. As well, if you look at the outside, it's mostly reflective on edge because water has a low refractive index, and so due to the Fresnel effect, it's mostly reflective on edge and not in center, and therefore you have to set up your lights quite carefully if you want to actually catch and observe this phenomenon. One other effect I might note is you see it kind of settles down. If you've ever looked closely at soap bubble films as they're about to pop, the soap film kind of settles down and you get the color, and it's just a few molecules, I think, in thickness holding on at the top, which becomes very transparent, and then finally it pops. Here's a simulation of rain on a window, and it's done again with, this is with 3D Maya fluids, but very thin grid. And emitting from particles. So I have the particles when they hit the fluid, they emit into it, and so you get the drops added. And the drops, the interesting emergent behavior is as the drops add up, they kind of build up and they create a cascading effect where then they get rivulets, and then the rivulets are joined by the drops in front of them. And of course on real windows you can see amazing patterns in the rivulets due to that. In my fluids, we also recently added the ability to have self-attraction of the fluid, and this is kind of unusual in a volumetric fluid solve to have self-attraction, but it's an interesting property, and it kind of simulates the way gases in space might behave. With gravity, the gas is pulled together. The gas in this case had an initial spin, so the resulting angular momentum keeps it whipping around and energetic, and you get like a little mini galaxy forming in 2D from the collapse and self-attraction. By allowing the fluid to be pulled together, we can create many interesting sorts of effects, and again you get tentacles and streaming kinds of shapes coming out of it that you wouldn't in the normal fluid simulation. This one I like to call the Eye of Sauron. And note, we also have auto-resize fluids, so the fluid container attempts to resize to fit the emitter I have here, as it and the emitter is also adding some spin as it pulls the fluid around. So starting with my own image, I can run a fluid simulation on it, a 2D one, and the self-interaction of the fluid creates all kinds of interesting possibilities. And so you have basically a fluid fractal of sorts it's really when you have the self-interaction that you get this kind of interesting behavior. And when you combine the self-attraction with a little bit of random noise, you can get a sustainable detail in the fluid that's very hard to achieve otherwise, and essentially you get a sort of a fluidic fractal. In addition to being attractive, the fluid can also be repulsive, or it can repel itself. We recently extended Maya fluids to handle liquids. I know that seems a bit ironic that Maya Fluids doesn't do liquids, but now at least it does liquids. In this simulation, Maya Fluids is, you can see it's solving with auto resize in the purple box. Now, a tricky thing about working with auto resize is tracking moving boundaries within the fluid voxel grid. So we have a fluid voxel grid, and because it's auto resizing, we're keeping the area, the number of voxels that we have to solve to a minimum, which is always a problem with fluids, at least voxel-based fluids, is the sheer number of voxels you have to solve. In this case, you can see as I move this, the purple box is trying to resize with it, and we're tracking the moving boundaries of the container so that there aren't any leaks, and we can spill it out onto the ground. So normally this kind of solution is handled either by particles or hybrid fluid particle methods. We're doing it entirely with a voxel grid method. Here's a play blast showing that at a somewhat higher resolution. One of the nice things about this as well is that we can handle notions of mist because we have a 3D volumetric fluid and we're pushing density around in it. We can also easily handle effects like color mixing within the fluid. Once again, we get a lot of complexity from simple starting conditions. And this is by the iteration of these small level rules over and over again. So in the case of the fluid, we're doing the Navier-Stokes equations at a voxel level, and then just iterating on those equations on all the voxels. There's lots of tricks, of course, in computer graphs. You have to simplify and do things to make it go faster because doing the true full simulation, because there are just so many points that you need to simulate, is too computationally intensive. We tend to take water for granted because we use it so much in our everyday life, but it is one of the most marvelous and complex substances we know of, and absolutely essential for life. So in this animation, I tried to get a sense of large water, which generally creates foam. So my first attempt was I put a bunch of holes in a grating and then squeezed the fluid through it, hoping to create enough bubbles within the fluid. Unfortunately, this particular fluid model I'm using is the air is completely compressible, so bubbles kind of collapse out from within it, so you can't sustain the fine bubbles in the flow that you need to get the white from the reflection. So to get around that, I just added some white on the shading of the surface of the fluid. Lava is a substance where we get remarkably complex behavior. In this case, I'm using Maya particles, and then the surface creating with the Maya particles is emitting a temperature from the particles that's affecting the shading of the surface that's created from the particles. So we'll use that to control the incandescence maps as well as an emission map where I'm emitting into a fluid for the flames and the smoke. As well, there's a displacement map on the surface to give the extra detail and bumping, and that's a nice displacement maps are a nice kind of simplification where we don't have to model every little tiny bit and bump as a separate particle or piece. One of the things that people frequently want to do with fluid dynamics is things that are you don't see in nature, and that typically involves going against entropy or the flow of entropy, where things happen in reverse directions. Sometimes you can do it by just backing up the filming it one way and then going backwards, but a lot of times that doesn't work right. So here I'm doing goals to pull smoke into the shape of Maya. And rather than pulling the fluid smoke into the shape, which is quite difficult to do, I'm instead pulling particles into the shape. And then the particles are emitting into 3D volumetric fluid to get a bit more natural motion. Now, perhaps you've heard of the Kessler Syndrome. This is a problem that could potentially befall us due to all the space junk that we have orbiting the Earth. The way it works is that there's so much stuff up there that at a certain point it achieves a critical mass where if two of the satellites collide, they spew out debris that then hits other satellites that breaks them up, and their debris hits other satellites, and eventually there's debris everywhere in a chain reaction, not unlike a fission explosion. Although maybe not, well, maybe worse in some ways. The kind of problem that could ensue if you have that, it could mean space would be unflyable. We wouldn't be able to launch anything for all the debris that there would be up there. And it's kind of hard to tell if we're at a critical point yet. Probably not, but maybe in the future we might get so much stuff up there that this could happen. Now in this simulation I've got a couple of particle systems that are intercolliding, and then when the particles collide they emit into another particle system a bunch of extra particles, and then you get debris. And an interesting thing you might notice is that you're starting to get from the explosions, which are yet another particle to do the flash when they collide, things are forming these chains, which is an interesting thing that one might not expect, but it's typical of what happens in broken up debris as it orbits and gets pulled out by the orbits. You naturally get this effect where debris forms long stringy chains. You might have noticed that in the breakup of comet Shoemaker-Levy around when it went into Jupiter, famously observed crashing into Jupiter. As you can see, this is starting to get pretty dramatic, and I don't know if I would want to be out in a spaceship flying around when something like this was going on. Now, in the midst of all this explosion and chaos, I'd like to come to the end of our presentation with what I think is the most complex item in the universe, the human brain. And this is a simulation I did of the formation of a brain, and it's using NCloth. Basically, it's a case of a type of emergence from simple conditions. So I start with that simple object at the beginning of it, and then kind of increase the rest length of the surface. So it wants to stretch out and occupy more space. At the same time, I'm constraining the volume of the surface, so it can't grow in volume. So then it has to form wrinkles if it can't grow in volume, but the surface area is increasing. And it also has self-collisions, so the wrinkles self-collide as they form. And additionally added a brain case to further kind of constrain the kinds of shapes it could form as it wrinkles. And maybe it's not such a bad model for the way the actual the wrinkles in the brain form as it develops from a fetal stage. But again, all those interesting wrinkles are something that you might not expect from just simply varying a few parameters in the simulation. And as I say, once again, the brain is a good stopping point here because we started with the simplest thing I could think of, and we end with what I believe to be the most complex thing in the entire universe. I thank you.